Imagine you reference a document by its fingerprint, but the fingerprint changes every time someone signs it. That's the problem Bitcoin lived with for years. Every signature altered the transaction's identity, and that single design choice nearly made smart contracts impossible. The fix, Segregated Witness, or SegWit, didn't just solve this. It gave Bitcoin a cleaner architecture and a path for future evolution. To understand the fix, we first need to understand what a witness is. In a courtroom, a witness provides evidence that something happened. In cryptography, the concept is similar but more precise. Consider the equation x plus 2 equals 4. The witness is x equals 2. Anyone can verify this. Plug 2 into the equation, compute 2 plus 2, get 4, and confirm it matches. The verifier doesn't need to find the solution, they just need to check it. Bitcoin uses the same pattern. Every transaction output contains a locking script. That's the equation. To spend those coins, you provide a digital signature. That's the witness. Thousands of full nodes across the network receive your transaction, plug your signature into the locking script, and verify that it holds. If the check passes, the spend is valid. Here's the critical part. The witness data, the signature, must be included inside the transaction so that nodes can verify it. In Bitcoin's original format, that witness data goes in the input script. A legacy Bitcoin transaction has 4 main sections. First, a version number, then a list of inputs. And inside each input lives an input script where the signatures are stored. Next, a list of outputs that specify where coins go. And finally, a lock time field. The transaction ID or txid is computed by hashing all of these fields together using double SHA-256. Every single byte, including the input script with its signatures, feeds into the hash. This txid is how Bitcoin's ledger tracks transactions. When a later transaction spends coins from this one, it references this txid. If even a single bit of the transaction changes, the txid changes, and every downstream transaction referencing the old txid breaks. This creates the first malleability problem, circular dependency. Malleability means the ability to change a transaction's encoding and therefore its transaction ID without changing its economic effect. Same inputs, same outputs, different identity. Here's the scenario. Alice and Bob want to open a payment channel. They'll each deposit 1 Bitcoin into a 2 of 2 multi-sig address, meaning both signatures are required to spend. But before committing funds, they need a safety guarantee, a pre-signed refund transaction that returns their coins after a timeout. The refund transaction must reference the funding transaction's ID in its input. But the funding transaction's ID requires both Alice's and Bob's signatures. Those signatures don't exist yet because neither party wants to sign the funding transaction until the refund is in place. This is a chicken and egg problem. You can't build the refund without the funding transaction ID. You can't compute the funding transaction ID without signatures. And you can't safely broadcast the funding transaction without the refund as a safety net. Consider a simple locking script. 2, OP add 4, OP equal. The witness, the value 2, can be encoded multiple ways. The opcode OP2 or OP push 1, followed by the byte 0x02. Both are valid. Both produce the correct result. But they're different bytes, producing different transaction IDs. Now picture a chain. Alice pays Bob, Bob pays Carol. Everything looks good. But a random network observer, a bystander, intercepts Alice's unconfirmed transaction, swaps OP2 for OP push 1, and rebroadcasts it. The modified version confirms with a brand new transaction ID. Bob's payment to Carol referenced Alice's original transaction ID, which no longer exists. That reference is now broken. Bob's transaction is invalid. Carol never gets paid. Nobody stole anything, but the entire payment chain broke. Same economic effect, different transaction ID, and the downstream chain is destroyed. Even if we eliminated every encoding ambiguity, a deeper problem remains. Digital signatures contain a random value called a nonce. Different nonces produce different valid signatures for the same message, mathematically correct but different bytes. In a multi-sig setup, Bob signs the same transaction twice with different nonces, creating two valid versions with different transaction IDs. If Alice pre-signed a refund referencing version A and Bob broadcasts version B instead, Alice's refund is dead. The transaction ID references never confirmed. This is second-party malleability. Your own cosigner can sabotage pre-signed transactions. Developers understood the root cause as early as 2011. All three problems trace back to one choice, including signatures in the transaction ID. The fix: exclude witness data from the transaction ID calculation. SegWit restructures the transaction format. Let's compare the legacy format on the left with the SegWit format on the right. In the legacy format, we have version, inputs plus the input script containing signatures, outputs, and lock time. The transaction ID is a hash of all of these sections, signatures included. Now in the SegWit format, we have version, inputs with the input script left empty, outputs, and lock time. But the signatures aren't gone. A new field called the witness structure holds them separately, outside the main body. The transaction ID hash covers only versions through lock time, but not the witness structure. Signatures still exist. Every node still receives and verifies them. SegWit does not remove signatures, it simply moves them. And with that one architectural change, all three problems vanish. Circular dependency, fixed. Third-party malleability, fixed. Second-party malleability, fixed. SegWit deployed as a soft fork, a backward compatible consensus rule change that makes rules strictly more restrictive, never less. SegWit outputs use a special template, a version byte followed by a witness program. Old nodes don't recognize this pattern. To them, it looks like an anyone can spend output, trivially valid. New nodes, on the other hand, recognize the version byte and enforce full witness validation. Same transaction, two interpretations, and both consider it valid. No node is forced to upgrade. Because the new rules are strictly more restrictive, soft fork compatibility is maintained and consensus holds across the entire network. SegWit isn't just a patch, it's the latest chapter in a pattern unfolding since Bitcoin's creation. Every version of Bitcoin separates authorization from authentication. Authorization defines who can spend. Authentication proves they have the right. Let's trace this evolution. In the original white paper, a public key authorizes spending and a digital signature authenticates the spender. In legacy Bitcoin, the system grew more abstract. An output script authorizes spending, encoding any condition, not just a public key check. An input script authenticates by providing whatever data satisfies that condition. With SegWit, abstraction increases again. A witness program authorizes spending, a compat commitment to the spending conditions. A witness structure authenticates by providing the full script and signature data. Each stage preserves the authorized and authenticate pairing while increasing flexibility. The output defines what's required. The input proves it's been satisfied. SegWit moved the proof out of the identity calculation. Same pattern, greater abstraction at every stage. With stable transaction IDs, Bitcoin gained the ability to build reliable chains of pre-signed transactions. First outcome: stable transaction IDs enable reliable pre-signed transaction chains. Second, the Lightning Network is now possible, with payment channels that support safe refunds. Third, a future upgrade path is established with witness versions 1 through 16 reserved. And fourth, Taproot, activated in 2021, already uses Witness version 1. Let's see this as a timeline. On the left, legacy Bitcoin, marked with a red malleability warning. At the center, SegWit in 2017, shown with a green shield and 3 check marks representing the 3 malleability fixes. On the right, Taproot in 2021, using version 1, followed by dotted boxes for versions 2 through 16, the future. An arrow runs across the entire timeline, labeled evolution without hard forks. SegWit didn't just fix transaction malleability, it gave Bitcoin a cleaner architecture and a path for future evolution,